Welcome to this explainer. Okay, today we're diving into something truly fundamental. Have you ever marveled at how a gazelle calf can just struggle to its feet and within like half an hour start running at 20 miles per hour? Or maybe you've watched an infant learn how to play with toys, wildly waving its arms and just intensely observing what happens. In both of those cases, there's no explicit teacher handing them an instruction manual. None. Instead, there's a direct sensory motor connection to their environment. They learn by interacting directly with the world. Today, we're going to look at how we can capture that incredibly powerful biological process and turn it into a computational approach. So let's dive right into this foundational concept. The approach we're talking about is called reinforcement learning. Unlike other forms of machine learning, where an agent is told exactly what to do, a reinforcement learning agent has to discover which actions give the most reward by actively trying them out. And the real revelation here is that it's a closed-loop system. The actions the learner takes directly influence its later inputs. You're basically mapping situations to actions to maximize a numerical reward signal strictly through trial and error. Here's our roadmap for today. We'll define the core reinforcement learning problem, break down its 4 internal elements, watch an agent learn tic-tac-toe, face the explore versus exploit dilemma, try our luck with a multi-arm bandit, and finally, trace the history of how this all came together. All right, let's kick things off with part 1, the reinforcement learning problem. Think about how you learn. There's a pretty stark contrast between evaluative and instructive feedback. In supervised learning, which, dominates a lot of AI today, an external teacher basically hands the system the definitively correct action. It's like having a cheat sheet. But in uncharted territory where learning is actually the most beneficial, you rarely have a perfect teacher. That is exactly where reinforcement learning shines. It relies on evaluative feedback. It tells you how good your action was, but not if it was the absolute best or worst action possible. Finding that out requires active, messy, trial and error search.
Moving right along to part 2, the 4 core elements.
To build an agent capable of independent learning, there are basically 4 essential gears turning under the hood. First up, the policy. This is straightforward. It's the rulebook the agent follows to pick an action. Then you have the reward signal, which is the immediate goal. Biologically, this is akin to an immediate jolt of pleasure or pain. But the real secret sauce here is the value function. This is your long-term foresight. Think of a reward as the immediate satisfaction of eating a donut right now. The value function is resisting the donut to hit your long-term fitness goals later. Estimating these long-term values is absolutely crucial and honestly the hardest part. Finally, we have an optional environment model, which lets the agent sort of simulate and plan for future situations in its head. Okay, let's see how this actually works in practice. Part 3, learning to play tic-tac-toe. Imagine we want to train an agent to play tic-tac-toe against an imperfect opponent. But we aren't going to teach it any strategies. Nothing. Without knowing any rules, our agent sets up a massive table of numbers. Each number represents its current estimate of the probability of winning from any given board state. 3 X's in a row, the value is a perfect 1. 3 O's, it's a 0. Literally everything else starts as a total guess, usually right down the middle, at 0.5. At the beginning of the game, there are so many possible moves, representing total uncertainty. So the agent starts playing game after game, evaluating its options. Most of the time, the agent takes the greedy route, meaning it exploits its current knowledge by jumping to the state with the highest estimated value. But here is the kicker. Every so often, it throws a wild card. It picks a move completely at random just to explore. This forces the agent to experience strange, unexpected board states it might otherwise completely ignore, which helps refine those early blind guesses into highly accurate predictions. Now, how does it actually update its guesses? It uses a brilliant core learning mechanism called a temporal difference backup. Basically, after the agent makes a greedy move, it takes the value of the new state it just landed in, and it backs it up to the state it was just in. It adjusts the previous state's estimated value just a fraction of the way toward the later state's value. So in real time, it is constantly tweaking its earlier expectations based on later realities. As the board fills up, these backups ripple backward, and this is the massive aha moment. By merely moving earlier estimates a fraction of the way toward later estimates step by step, the system actually achieves the effects of complex planning. And it does all of this without needing to compute massive, explicit forward searches through thousands of future possibilities. It is just incredibly efficient. Over many, many games against our imperfect opponent, this super simple fractional update method naturally converges into a master strategy. Honestly, it's almost eerie to watch. Purely through trial, error, and adjusting values, the machine learns foresight. It naturally starts setting up complex, multi-move traps for a short-sighted opponent, acting as if it had been given a brilliant strategic manual all along.
Which perfectly sets up Part 4, Exploration versus Exploitation.
Mastering a simple game like tic-tac-toe exposes a fundamental conflict that literally all learning agents must confront. Do you exploit what you know, or explore the unknown? Think of it like this. Do you go to your favorite restaurant and order the dish you know for a fact is absolutely amazing, exploiting what you already know? Or do you try that brand new place down the street, risking a bad meal for the chance of discovering a new all-time favorite, exploring the unknown? The catch is, you can't do both at the same time. If you only exploit, you get stuck in a mediocre rut. But if you only explore, you never actually reap the rewards of your discoveries. Let's look at how the math handles this dilemma in Part 5, the multi-armed bandit. Mathematicians study this exact problem using a thought experiment that's basically a Vegas casino slot machine with multiple levers, known as the N-armed bandit problem. If you use a purely greedy method, always pulling the lever with the highest estimated payout, a short string of bad luck early on might make you mistakenly abandon the best lever forever. You just fail to find the optimal action. But look at the epsilon greedy method. Here, you act greedily most of the time, but with a tiny, tiny probability, you pick a lever completely at random. When we compare these methods in simulations, the results are staggering. By injecting just a tiny drop of randomness, the epsilon greedy method forces the agent to keep checking all the options, asymptotically guaranteeing it will eventually find the true optimal choice. And finally, Part 6, 3 Threads of History. To fully appreciate modern reinforcement learning, it is absolutely wild to see how disciplines that rarely even spoke to each other ended up building this entire field. The first thread started way back in the late 1800s with animal psychology. The second thread is highly mathematical, originating in the 1950s with Richard Bellman formulating equations for dynamic programming. And the third thread dealt with predicting secondary reinforcers over time. For decades, these threads ran strictly parallel. Then came the ultimate Avengers assembling moment of computer science in 1989. Researcher Chris Watkins developed Q-learning, beautifully weaving these psychological intuitions, control equations, and temporal difference algorithms together into the modern powerhouse that we use today. I actually want to quickly highlight that psychology thread because it's just so beautifully intuitive. This is Edward Thorndike's Law of Effect from 1911. It perfectly captures the biological core of trial and error. Basically, what brings satisfaction gets wired in. What brings discomfort gets wired out. Wired in, wired out. Over 100 years later, this exact fundamental observation about animal behavior is the literal logic driving artificial agents to master complex tasks. So, as we wrap up this explainer, I want to leave you with a thought. We've seen that for a machine to truly learn, to find the absolute optimal path, it cannot just exploit what it already knows. It must inject randomness. It mathematically has to explore the unknown to avoid getting stuck in a local maximum. So ask yourself, if an algorithm mathematically requires exploration to succeed in the long run, where in your own life should you be exploring a little more, instead of just exploiting the same routines you already know? Thanks for joining me on this deep dive, and I'll catch you on the next one.